Hi, this is a little quick video on tutorial 8 question 1b. So this is a vector line integral along a particular vector field, and so you can sort of expand like this. So just do the dot product of xy with dx dy to give this sort of line integral. And there's a line integral on the curve, a straight line from 0, 0 to 3, 3. So first of all, I think I would check for is to see if the closed curve two endpoints match up. They don't. If they did, green's theorem would be a good idea, but not applicable in this case. So the next thing to try to do is to try to check if it's a conservative function. So if it's conservative, then you let p be the first component, x in this case, and q be the second component, y in this case. Then to check it's conservative, you do the opposite partial derivatives to the order and take the difference. So q of x here is partial derivative of y respect to x gives you nothing. And then p of y, partial derivative of x respect to y, again gives you nothing. So if you take the differences, you get 0. So if the difference of these mixed partial derivatives is 0, then that implies it's a conservative function. So when it is a conservative function, then the fundamental theorem of line integrals applies. And that means, in particular, that this function, capital F here, can be written as the gradient of some potential function, little f. And the gradient of this little f would be partial with respect to x, comma, partial with respect to y. And we know that's going to equal keep capital F here. First component is x, second component y. And now we know this, well, we can just try to solve it. So if little fx equals x is our first equation, and our second equation is little fy equals y. So just do them one at a time. So let's just do the first one. So the first one we take partially integrate both sides. So partial integral of x gives you f, of course. Then we integrate with respect to x. So integral of x gives you x squared on 2. And then you have to put a plus c down. Now, this plus c means constant with respect to x, because it's partial integration. But it could be a function of any other variable. So there is y's floating around. So in general, f would have a function of y as the constant here. In order to bring this second equation involved, let's take the partial derivative with respect to y, this one here, and equate it to what we've got to make sure it all works out. So the partial derivative of the first term with respect to y just kills it, goes to 0. Partial derivative of the second term would be the straight normal derivative with respect to y. And from this equation, that has to equal just y by itself. So now integrating, this is just a function of just one variable, so no tricky partial integrals anymore. We can integrate, so cy then would be y squared on 2 plus a constant. And since it's just and this is constant with respect to y, we already know there's no x's around, so that's the end of it. So our potential function is then x squared plus y squared on 2 plus any constant we want. We might as well let k be 0 because that doesn't really matter what it is, and that's our potential function. And so by the fundamental theorem of line integrals, this integral here is pretty much the potential function, so x squared plus y squared on 2, subbing in the endpoints. So the first endpoint was 0, 0, second endpoint was 3, 3. So if you sub in 3, 3, you're getting its distance squared. So 9 plus 9 divided by 2 gives you 9. Sub in 0, 0, you get nothing. And so the value of this vector line integral is 9, using what's called the fundamental theorem of line integrals. So that's the way to do it comprehensively. And indeed, if you've got any vector line integral, it's not closed, check if it's conservative, and you can do this sort of approach. In this particular case, you could do some shortcuts though, and it's worthwhile mentioning it. So if you go back to the original vector line integral, was integral of x dx plus y dy. Now in this case, instead of doing the the fundamental theorem of line integrals explicitly, you can do it implicitly. And notice that this term here, you're integrating respect to x, there's only x's present. So this is no mixed variables. We could just integrate that separately. And so integral of x respect to x would be x squared over 2. And for the limits at x is x equals 0 to x equals 3. And what I'm really doing is I am appealing to the fundamental theorem of line integrals so more implicitly. So x squared on 2 is the potential function corresponding to x comma 0 effectively. There's another term, and again this y here, so the integram for the dy part has only got y's in it, so we can do the same sort of trick and integrate just that term with respect to y and sub in the endpoints for y. So again, plugging the limits in, you get 9 and 2 for the first one, 9 and 2 for the second, giving you a total of 9. Now that way was certainly quicker in this case. I mean, I can do the whole thing in 3 lines, so to speak. But the former approach, which had involved working the potential function, certainly is important, needed in other more complicated cases. So it's good to know the more general method. But it is okay. So the whole theory justifies this latter approach. So that I hope helps seeing the fundamental theorem of line integrals.